We'll wrap up Chapter 2 with Section 2C, some problem-solving guidelines and hints. I consider this section sort of like a puzzle section. Some of these are puzzling questions and you have to determine a way or a pattern or a strategy to use to solve them. And there may be more than one strategy. The way I work it may not be the way you work it, but if we come to that similar conclusion, that's the most important thing. In some cases, there may be more than one answer, so we want to keep that in mind. This is probably different than any other math class you've taken. Choose the appropriate tools. Let's see, maybe a diagram is going to help you solve it, or maybe creating a table using some device to help you solve it. Yeah, there are lots of tools available. If the problem seems too difficult, then try it with a simpler, smaller problem. A simpler, similar problem. Approximations can be very helpful. Try a different way of thinking about it. And finally, the last one is don't spin your wheels. If you get aggravated, get up, walk away, and then come back, and you may just have a fresh perspective, and the strategy may just pop out at you immediately. So always take a break if you're solving a problem and you get frustrated. So here is a problem. Imagine a mile-long bar of metal, such as the rail along a railroad track. Suppose that the rail is anchored on both ends, a mile apart. So we've got this long rail anchored on both ends, and it's a hot day. And we are told that the length of that rail expands. Now remember, that rail is 1 mile long. It expands by 1 foot in the hot sun. So if the added length causes that rail to bow in the middle, bow upward in a circular arc, about how high would the center of the rail rise above the ground? The fact that I see the word about how high means we're probably going to have to do some approximations. What's really cool is to try and guess what you think the answer will be. 1 mile piece of steel. Its length increases by 1 foot, but it's anchored on both ends, so that increase in length causes it to bow in the middle. So we're basically adding a foot to a 1 mile piece of steel. My question to you is, write down how high you think that rail is going to be when it bows in the middle and lifts off the ground. Do you think it's going to be inches, feet, yards, miles? How high do you think that rail will be off of the ground? So let me just draw a quick little diagram. So we've got a piece of steel that's 1 mile long, and it's anchored on both ends. And in the hot sun, this rail is going to bow towards the center to the sky and leave you with an arc. So the original length of that piece of steel is 1 mile, but increases by 1 foot to 1 mile and 1 foot. So how high do you think the steel will rise? Think about that. Okay, so did you make your guess? I hope you did. I hope you made just a random, somewhat intelligent guess based on the information given in this problem. Now let's develop a strategy to approximate about how high it would be in the center of the rail. When I see this problem, I look at it, and I would need to know a lot of trigonometry to work with the circular arc, and my trig skills just aren't, right there. So I'm going to kind of try to come up with a different strategy. What I notice is I'm trying to find this height in the center, and if I look at this height and the bottom of the rail, it forms a 90-degree angle. And I know if I can form a 90-degree angle, I might be able to form a right triangle. And right triangles are easy to work with because we've got a good old Pythagorean theorem to work with. That's an easy formula to work with. So if I drew from the anchored end upwards to that high part in the middle, the top of that bow, I could form a right triangle. So I'm going to actually use the method of working with right triangles to help me find an approximate height to this rail. So think about a right triangle. We know Pythagorean's theorem. Oh, maybe you forgot it, so I'll tell you. It's a squared plus b squared equal to c squared. And remember, A and B, these are the legs of the triangle. C is always the hypotenuse. And remember, the hypotenuse is the side that's across from the right angle. All right, phone, be quiet. All right, I turned my phone off, so I won't get any more notifications. All right, so in this right triangle, the height is one of the legs. I'll just call it A. The bottom part, along the ground, if you will, would be B. That's another leg. And C would be the side across from the right angle. It would be the part that we're having emulate that bow in the rail. So across from the right angle would be my hypotenuse. And I actually have some values I can put in for part B and part C. Think about that. So let's give some values. Remember, A is the height of that triangle. That's what we're trying to find. The value of B, which is on the bottom of that triangle, is going to be half of the original size of that piece of steel. So the piece of steel was 1 mile, which is 5,280 feet. So half of that would be half of 5,280 feet. So side B is half of 5,280, which is 2,640 feet. So that's the base of my triangle. Now side C, we're using that to emulate that bow, half of that bow, when the rail lifts and bows upward. We're using the hypotenuse of the triangle to approximate side C. Now we know that when the rail bowed up, it increased in length by a foot. So this whole bow is 5,281 feet. But if I cut that in half, then that would give me half of this arc, and half of 5,281 is 2,640.5. So I have side C, I have side B. All I need to do is put B and C in the Pythagorean theorem and solve for A, which is the height. So I'll have A squared plus B squared, and remember B was half of that base, 2,640, I have to square it, equal to C squared, 2,640.5 squared. So A squared plus B squared equals C squared. Well, if we do some arithmetic and we square, we're going to have to solve this for A squared, which means we're going to have to bring the 2640 squared to the other side and subtract it from the 2640.5 squared. Let's get that value. So A squared is equal to, now remembering your order of operations, you have to square the 2640.5 first, square the 2640 next, and then subtract those two results. So you have to square them individually, then subtract those two results. Definitely want a calculator handy. And the result comes up to be 2,640.25. So that's what A squared is equal to. And if you remember working with quadratic equations, yes, I said it. I said a quadratic. A little algebra's coming into play here, but this isn't difficult algebra. To solve an equation that has a square, you have to square root both sides of that equation. So the square root of A squared is A. That's why we square rooted it, because a square root undoes a square. Now find the square root of 2,640.25. So doing the arithmetic, we get 51.38. And that's the value of A. And remember, A represents the height of that triangle. So that's the height of the bow in the middle of that circular arc. That's not the actual value. Remember, we're approximating. Let me tell you, you might think, oh my God, that's an incredible amount. This piece of steel that's a mile long only increased in length by 1 foot, but it ends up being 51 feet high in the middle. How does that happen? Well, the arithmetic is right. The actual value, since we did some estimating, this isn't 100%, but the actual value is about 42. I think it's 42 feet if we use some trigonometry. Still, isn't that an incredibly high value? But all the arithmetic is done right. Our estimation was pretty decent, 51, but it's actually 42 feet. So that 1 foot increase in the length of that 1 mile piece of steel would cause it to bow, and in the middle of that bow, it would be 42 feet. Pretty incredible, huh? Well, let's take a look and answer a couple of questions. First, are you surprised? Yes, I was surprised when I did this. 42 feet, really? How does the use of approximation tell you that the original question contained at least some unrealistic assumptions? Well, let's go back to the top and see what are some of the assumptions. One of the assumptions is that we have one piece of metal that's continuous for a mile. That's an incredibly long piece of metal. I don't know if something like that could be manufactured. Also, think about a railroad system. It doesn't contain a 1 mile long continuous piece of steel. It has steel in certain sections, and I'm sure those sections are there to compensate for the expansion of metal. And then another situation is, would it expand by a foot? We don't know the coefficient of expansion for metal, so maybe the assumption that it expands by a foot might be off, or the fact that we have a continuous rail for a mile, that assumption may be wrong. So here is the moral of the story. You may work a problem, you may come up with an answer that mathematically is correct, the numbers are correct, you get a decent estimate, but something seems way off, then you should go back and look at the original problem and see, was there something there that I am missing, or was there an assumption there that actually might even be wrong or unrealistic? Okay, so there's an example of a problem. We used a strategy, we solved it, and then we realized, let's go back and take a look at the original and see what might have been unrealistic. Okay, so take a second, read example 2, see if you can figure that one out, come up with a solution. Well, I hope you solved it and came up with a solution. Now let's see if your solution is correct. It says it takes us 30 seconds to walk from the first ground floor of a building to the 3rd floor of that building. The question is, how long will it take you to walk from the 1st floor to the 6th floor? So from the 1st to the 3rd, it's 30 seconds. How long would it take you to go from the 1st to the 6th? Pictures always help me. A diagram helps me figure this out. So in my picture, I have a line at the ground floor, which is my 1st floor. And then above that, I drew a line for the 2nd floor, above that a line for the 3rd, above a 4th, above that for the 5th, and above that for the 6th floor. And the problem tells me it takes 30 seconds to go from the 1st floor to the 3rd floor. So from the 1st floor to the 3rd floor, it takes me 30 seconds. Well, I didn't walk up 3 flights, 3 floors. I only walked up 2. I went from the 1st to the 2nd and the 2nd to the 3rd. So if that took 30 seconds, then it should be 15 seconds per floor, because I only walked up 2 floors. So 15 seconds per floor to get from the 1st to the 3rd. Well, once I figure that out, then to go from the 3rd to the 4th is 15 seconds. From the 4th to the 5th is 15 seconds. And from the 5th to the 6th is 15 seconds. So if I added all that up, how long is that? So if I multiply 15 times 5, I would get 75 seconds which is about 1 minute and 15 seconds. If your answer was wrong, then you probably didn't take into account that the first floor was on the ground floor, and to get from the first to the third, you only had to walk up 2 floors or 2 flights of stairs instead of 3. All right, let's go on. Here's the next example. We've got 5 runners: Andy, Beth, Dale, Ella, and Tree. They're in a 1-mile race, and here is the information on how they finished. Andy finished 6 seconds before Beth. Beth finished 3 seconds before Tree. Tree finished 5 seconds after Dale. And Dale finished 7 seconds after Ella. The question is, in what order did the runners finish this race? Figure out a strategy. You might want to use a tool or device that's going to help you put these folks in their correct positions. And hint, you might want to use a number line. So give it a try. Using a number line, I can get started with this problem. I'm going to start with the first thing that's mentioned. Andy finished 6 seconds before Beth. So on this number line, I'm going to put Beth just anywhere, mark a spot. And Andy finished 6 seconds before her. So I'm going to go 6 seconds behind her. I'm going to go left 6. 1, 2, 3, 4, 5, 6. So that's 6 seconds. And that Andy is 6 seconds ahead of her, before her. Now try to finish it. So did you figure it out? If you started with Beth and went back 6 seconds to Andy, that was a good start. Then Beth finished 3 seconds before Tree, so where you had Beth marked, you need to add 3 seconds for Tree. Then Tree finished 5 seconds after Dale, so I would have to back up 5 seconds from Tree to get me to Dale. And Dale finished 7 seconds after Ella, so I would have to back up 7 seconds to get to Ella's finishing time. So you can see the order: Ella's first, Andy's second, Dale is third, Beth is fourth, and Tree is fifth. So to me, this is kind of like a puzzle problem. Try the next one. Kathy stood on the middle rung of a ladder. She climbed up 4 rungs, moved down 5 rungs, and then climbed up 5 rungs. Then she climbed up the remaining 4 rungs to the top of the ladder. How many rungs are there in the whole ladder? And use a diagram to help you. Alright, so the solution I got was 25 rungs in the ladder. And I started here with marking a spot in the middle on my diagram, and then from that middle I moved up 4 rungs, and then from that stopping point I went down 5. From that stopping point I went up 9, and then from that spot I climbed up the remaining 4 rungs to get to the top. Once I had all those marks for each rung, I was able to see where my middle point was, count how many rungs I had above my middle point, assume I had that many below, so I had 12 rungs on top, 12 rungs on the bottom, and the one in the middle gave me 25 rungs.